We're picking up on exit ticket 16-4, weak acids and bases. Excuse me, haven't talked in a while. We're going to pick up where we left off last time with the idea of acid strength. So we're going to talk a little bit about strong acids now, and then we're going to talk about weak acids. And then we'll pick up with strong bases and finish out with weak bases. So we talked about strong acids last time we met, where we know that some acids dissociate in water into their ions very easily, and for these acids there's no equilibrium. We end up with all product, completely ionized acid into H3O plus and an anion that goes with that. After the reaction, only products remain. These are those 6 strong acids that we talked about last time. They went onto your exit ticket last time, but you might want to get them onto your cheat sheet to remind you that when you see these 6 acids, they're very simple to solve for. For a strong acid, the H3O plus concentration, also called the H plus concentration, is the concentration of the acid. So if you know the molarity of HCl, and you know maybe it's 2 molar HCl, then you have 2 moles of hydrogen available because it completely dissociates. So let's do a few calculations together. First of all, we look at the acid and its molarity. This is a strong acid. It's hydroiodic acid and it's 0.15 molar. So that because of what we just said, for strong acids which completely dissociate, the H3O concentration is 0.15 molar. Likewise for this one. It's a strong acid, so the concentration is 0.0235 molar. This one, HCl, another strong acid, so this becomes 2.50 molar. And the last one's a little bit different. We've got H2SO4. For every mole of this acid, you get 2 moles of H3O plus or H plus ions dissociating. So we are going to double this and call this 5.0 E minus 3 molar H plus ions. And that's what we've got for that one. To do the OH, we use the the thing we did last time, where we take the equilibrium KW relationship between the OH and the H plus and use that to solve for this. So you say that 1.0 times 10 to the minus 14th divided by this will give you the OH concentration. And then for pH, we take this and take the negative log of the H3O plus concentration. Remember, pH is the power of hydrogen concentration. So strong acids completely break apart into H3O and an anion. So there's no equilibrium expression because there's no equilibrium, which makes it really easy. Hang on, I got to deal with my kid. Okay. So weak acids don't completely break apart. Some of them will go to product and some will stay as acid, and some of the product converts back to acid, so you do have an equilibrium. You've got this weak acid breaking into the H3O and an anion, but you have the reverse going on at the same time, so now we have to have an equilibrium constant. The equilibrium constant expression for a weak acid, Ka, is the H3O concentration times the anion concentration over the weak acid concentration. So we'll get to apply this in a moment. Just remember that the larger the value of Ka, the stronger the acid is, the more the reaction goes to the right. So all acids that are not strong, there are 6 strong acids you have to know. The rest are weak acids. Things like acetic acid, which is vinegar, citric acid, which is used to make candy sour, carbonic acid in your bloodstream. These all have equilibria associated with them, and they have an equilibrium constant. Note that in any problem for chemistry class you're going to do, if there's a Ka associated with the acid or base problem, you are dealing with a weak acid. So if there's a Ka in the problem, you know you're using these mathematics. So let's take an example. Calculate the H3O plus of 1.5 molar HNO2, not HNO3, HNO2 with an equilibrium constant for the weak acid of 4.0 times 10 to the minus 4th. Remember, there's no units on that. Let's look at this equation. We've got a weak acid and liquid water. That should have an L, and H3O and NO2. So we want our products in the numerator and our reactant in the denominator. And we have a Ka. So Ka equals 4.0 E minus 4 equals, we know our denominator has a concentration of 1.5 molar, 1.5, and the numerator is this times this, and they're going to be the same as each other. When a mole of HNO2 dissociates, it makes a mole of each of those as well. So they're the same as each other. So we're going to call each one X, and X times X is X squared. And then you do the algebra to solve that equation. You want to get 1.5 out of the denominator by multiplying both sides by 1.5. And then you'll take this and take the square root of it. And when you do all that, you will end up with a concentration of 0.024 molar H3O plus. And that's how you do it. Is this one I just did? Oh, this is the one I just did. Yay! Okay, I did that. Now we're going to talk about base strength. So back on your exit ticket, you should be on number 5. Strong bases dissociate completely into OH minus and a cation. So now we've shifted to bases. And we're saying strong bases are like strong acids. They completely dissociate. The strong bases generally contain hydroxide, but be careful, some are di-basic. There's 2 bases per molecule, 2 OHs, 2 OHs, 2 of them. So the OH concentration will be twice the base concentration. Multiply the molarity of the base times 2 to get the molarity or concentration of the OH minus. So here's some examples. In this case, this has 1 OH, so it's 0.25 molar. This has got 1 base, so it's 0.0535 molar. This has 2, so 2 times 2.5 is 5.0 molar. This has got 2 OHs, so it's 2.5 times 2 is 5.0 E negative 3 molar. Then you'll be able to calculate and fill this in on your exit ticket. Find the H3O concentration from the KW equation. So in this case, you'll say 1E negative 14 divided by 0.25 equals, and the first one comes out to be 4E negative 14. And then you just hit negative log of that, and you'll get the pH, and this is 13.4. I'm going to let you work out the rest of those on your own and get that onto your exit ticket before you turn it in. All right, number 8 and 9 on the exit ticket. Strong bases completely dissociate in water, and only products remain. The equilibrium expression between reactants and products is going to be expressed as Kb equals the OH concentration times the concentration of a cation over the weak base concentration. We'll solve these just like we did for Ka. So here's an example. Calculate the OH minus concentration of a 3 molar NH3 with an equilibrium constant for the base of 4.8 times 10 to the minus 5. And there's the equation just to remind you. The liquid H2O does not get put into the expression because equilibrium expressions never have liquids or solids in them. So what are we going to do? We're going to say 4.8 E minus 5 equals X squared, because it's this times this. We don't know either one, but we know whatever they are, they're going to be the same, over the concentration of the base, 3.0 molar. And then you're going to get 3.0 out of the denominator. Sorry about the crummy writing, but it's really tough on this surface. So once you get to there, you'll have, let's see, you're solving for OH. The OH concentration will equal, when you get through all that and taking square roots, 1.2 E negative 2 molar. And then you're going to use the OH to calculate the H plus. 1 E negative 14 divided by 1.2 E minus 2 equals, we came up with 8.3 E negative 13, 8.3 E negative 13. You could take a PH of that if you want to do it. There's one more problem for you to do. I'm going to let you do that on your own, and if you want to check your exit ticket with me, you may do that before you finally turn it in. All right. I think that's it. Yeah.